Okay. So I am Eric Stotzer. I am with Texas Instruments. And some of you may be asking, Texas Instruments, what kind of, why are you here? And so we've been developing high-performance processors for the embedded space for quite a while now. This slide here is just giving you an example of where some of those application spaces are. Really, a lot of the processors that we're using in the HPC space have come from our telecommunications infrastructure space. So when you're talking on your cell phone and you're out, you're seeing all these antennas that are all over the place. At the bottom of those antennas are these things called base stations, because they're at the base of the antenna, so you would, of course, call them a base station. And inside there are a lot of DSPs doing a lot of specialized high-performance computing. And so we've tried to adapt those digital signal processors to the high-performance embedded space. And what's made them, I'll get to that here, is that what's made them a little easier to use is that we've put ARM cores on there to give a friendlier interface so that you can run something like Linux and then offload your code to the DSPs for signal processing and high-performance compute. So we have an architecture that we call Keystone, which is basically a system-on-chip architecture where we can put in ARMs and DSPs and graphics processors, and those what you're seeing on the left. And then on the right, you have things that are specialized or hardened accelerators. So one of the very first ones that we had, or the first family, was at that point DSP only, and we called that Keystone 1. And we worked with some people at looking at how you could use this for not traditional, I guess, signal processing stuff. And it was interesting. We have 8 DSPs on there. We have single precision floating point, double precision floating point. And there was some research done by some people at KTH where they started looking, hey, what if we ran LINPACK just on these DSPs? What kind of power and performance would we get? Because they were originally designed for embedded systems where power was important. And they got some good numbers. So this is sort of how we evolved into getting into this space. At that point, and still today, you can buy these boards that have lots of DSPs crammed on them, and then it's your typical kind of PCIe slot that you put them in. But then we came out with Keystone 2, and this is the device that actually added the ARM processors on there. So now you've got 4 ARM A15 processors along with the 8 DSPs. There were some other things added. There were some increases in some of the memory sizes. And now this chip became even more interesting because you could build a real system just based around this chip. It's not a PCIe sort of chip or SoC. What's also interesting is that the DSPs and the ARMs, they all have access to the same shared memory. So it's not offloading across a bus. They can access the same memory. So then we started working with vendors. People became interested. So probably the one that might be most applicable to traditional HPC would be what's going on with HP and their Moonshot system. So they have a cartridge now that they can plug in their system that is built around this SoC. There's others. There's Brown Dwarf, which is more uses this ACTA chassis, which is from telecommunications space, but trying to adapt it to more of a general purpose computing environment. There's also these little EVMs, the TI cells, that you can use if you just want to evaluate it.
What's EVM?
EVM is an evaluation module. So in the embedded world, you're going to build your own specialized stuff. You can buy these little boards from TI, do your software development, and then build your hardware. So they're called EVMs. So we looked at this like, well, this is very similar to a scalable model for heterogeneous programming. You can run MPI on the ARMs, and when the process lands on the ARM, you can then offload the highly intensive parts to the DSPs using something like OpenCL or the OpenMP accelerator model. So this is what we've been working on at TI, is we've been working on the OpenMP 4.0 support. We like I just said, we use the target regions to we're running all the code on the ARM, and then we use the target regions to offload code to the DSPs. So currently, this is where we're at. OpenMP 3.0 support is available on the device I showed you earlier, Keystone 1, that has just the 8 DSPs. So we run a bare metal implementation of OpenMP on the DSPs. Bare metal meaning there's no operating system under there. Our OpenMP runtime runs right on top some low-level API functions that we have for the DSPs. Then for Keystone 2, what we've done is we've taken that implementation of OpenMP and we've added the device constructs support for out of OpenMP 4.0. So now you're running OpenMP on the ARMs and then you're offloading regions to the DSPs using the 4.0 constructs. We're currently working on, we're kind of skipping 3.1 and just working on supporting 4.0 completely. And if you'd like to learn more or see some of these pieces of hardware that I've shown you, then please come by the Texas Instruments booth at 3745. Thank you.